All right, it's time for lecture B. Let's start by looking at this thing on the board here, and then we'll do some examples. So this is a theoretical, very important theoretical description of how to think about infinite series. An infinite series is just a thing that's like this. You might just call it an expression. You can write it with an infinite sum, where you've got an infinity up there, or you can write it with, where you write out the terms that are being added and you put plus dot dot dot, indicating that you imagine the sum is going on forever. You imagine this is an infinite sum, even though nobody can literally add up infinitely many things. Okay? But it turns out to be useful in many situations to pretend you can, and we need to describe what that pretending really means. What does it mean for a series like this to sum to something, to converge to something is the more official way to say that. You consider the corresponding sequence. This is not a summation. This is a list of numbers, S1, S2, S3, S4, etc., that are formed by summation, so they're called partial sums because you're adding up the series part way. That's why they're called partial sums. Not related to partial fractions. S1 is just the first term that you're adding, A1. S2 is the sum of the first two terms. S3 is the sum of the first three terms. S4 is the sum of the first four terms, etc. In general, Sn is the sum of the first n term. K goes from 1 to n. This is supposed to be a K here. It is a finite sum, so it is an actual sum, no pretending there going on. But that's a list of numbers, an infinite list of numbers. You can go forever. Does that sequence converge or not? If it does converge to something, then you say the series converges to that same thing. And you say it equals that thing. Like I said, if this sequence converges to 20, I could write if Sn converges to 20, we say the series, the infinite series, also converges to 20. And we write that it actually equals 20, pretending like we've actually added up infinitely many things. Put an equal sign there, even though any finite partial sum might not equal 20. Could equal 20 sometimes, but it very well may not ever equal 20 for any finite partial sum. But the limit exists and would be equal to 20, and so we go ahead and we write 20, that it equals 20, as if we added up infinitely many things. Let's consider some examples. We already considered the example where we were adding up 1 over k squared plus k. It was the example where we did partial fractions to help us figure out what the sum was. I think it was Monday's class lecture. What was that lecture, 21 or 22? I forgot already. 21? Okay. Let's consider a similar example that looks simpler. Add up the values of 1 over k squared. Not 1 over k squared plus k. It looks simpler, but it actually is tougher. You can't do anything with partial fractions to help you figure out a formula for the partial sums. You can still define the partial sums, and for any particular partial sum, you can compute it. You're adding up reciprocals of perfect squares here is what you're doing. So S1, the first partial sum, is just 1. S2 is the second partial sum. It's 1 plus a half, which is 3 halves. S3 is 1, oh, sorry, it was 1 plus a fourth. 1 plus a fourth, which was 5 fourths. S3 is 1 plus a fourth plus a ninth, getting a common denominator of 36. That is 36 plus 9 plus 4 over 36. It's 49 36ths. I've not made a mistake. It is interesting that both of those are perfect squares. This is 7 6 quantity squared, though I don't think that happens in general. Let's try one more by hand. 1 plus a fourth plus a ninth plus a 16th. This time we get a common denominator of I think 144 is going to work. 144 plus 36 plus the 16. 16 plus 9 over 144. That simplifies to what? This plus this is 180 plus that's 196 plus that is 205 over 144. And that cannot be reduced further. The 144 is a perfect square, but not 205. Etc. There's no clear pattern here to what these numbers are. And indeed, as far as I know, there's no simple formula for these partial sums. The nth partial sum, as far as I know, has no simple formula. Does the series converge or not? We're about to look at numerical evidence for whether or not it converges, but you should understand that this numerical evidence is definitely not a proof, one way or the other. In Mathematica, I can define a function s of n to be the nth partial sum of this. I can use the summation button and type it in like this. And then I can, for example, do a manipulate even. I can use table as well to look at a table of values, but I can also just manipulate. I can get numerical approximations to these values as n goes from 1 to, say, 100 in increments of 1. I need to add the extra comma 1 there to make sure n goes up by 1 each time. Otherwise, manipulate assumes it's a continuous variable, and I don't want that here. N is the number of terms in the sum. So there we go. When n is 1, it's 1, like we already knew. When n is 2, it's 1 plus a fourth, which is 5/4, or 1.25. When n is 3, what was it? It was 49/36. 1 and 13/36.
It's 1.361 repeating.
There we go, you're right. That's S3. Then I add on another, what, 1/16? We get up to that. Then I add 1/25th, then 1/36th, then 1/49th, then 1/64th. I keep adding the reciprocals of perfect squares here. And I keep going. The numbers keep going up. I'm generating a monotone increasing sequence. However, even though they keep going up slower and slower, there's no guarantee that this series converges. There's no guarantee that the sequence of partial sums converges. If I go out, say, even 10 decimal places, do all the decimal places settle down by the time little n is 100? Nope. What if I let little n go to 10,000? When we get to 10,000, it looks like it's perhaps only settled down to, say, 3 places after the decimal, but that's no guarantee. How do you know you're never going to get above 1.645 here? Maybe you do eventually if you let n go to 1 million, for example. We've got some evidence that this series sums to something finite because those partial sums keep going up slower and slower. You notice they go up fast at first, relatively speaking. But that's no proof one way or the other. Now, it turns out that I do know the answer here. And Mathematica knows the answer as well. This will calculate the limit of those partial sums. And I believe Mathematica will produce an answer here. You ready? It's going to be surprising. It's pi squared over 6. Well, of course, pi squared over 6. Why not? What? Pi? With perfect squares? Where are the circles? I don't see any circles. Pi squared over 6? Really? What is pi squared over 6? equal to approximately that. So evidently, if you do go out far enough, this 8 does become a 9, but the 4 never becomes a 5. That is the answer, pi squared over 6, though it took a genius named Euler to figure it out. Don't say Euler, say Euler. Not Euler. That hurts my ears. Euler is how you say that. It took his genius about 250 years ago to figure it out that the answer was pi squared over 6. It really was an ingenious method that he used to figure it out. We're not going to go into it. But that is the answer. So it does converge. Is there a way we can figure out for sure that it converges without just trusting Mathematica or trusting Euler? Turns out there is. We can prove this converges another way. I'm not really going to do an actual proof here, though. I'm going to do two calculations that are related to each other to make it plausible that it converges. These numbers, 1, a 4th, a 9th, a 16th, a 25th, can be thought of, if we want, as areas of rectangles, if we want to think of them that way. In fact, I'm going to ignore the 1. I'm going to focus starting on the 1/4, making rectangles of those heights and a base of 1 so that the area will be those values. In order on a number line, with the rectangle of height 1/4 being the first one. So this is going to be 1/4 here. That'll be my first rectangle. Its area, base times height, is 1/4. Ignoring the 1, that's the second term of the series that we are adding. For your next rectangle, make it have a height of 1/9. For the next rectangle, make it have a height of 1/16. The numbers we keep adding here, the terms in the series. Then 1/25th, then 1/36th, etc. Get a bunch of rectangles going on forever. The area of this is A2, A3, A4, A5, A6. Those rectangles go on forever. Their sum, if you could add up all those areas, would evidently equal the sum there starting at 1/4. Now, if we can't figure out what this sum equals without asking Mathematica or Euler, we're not going to be able to figure out what that sum equals without asking Mathematica or Euler. However, if we are careful to realize that the total area of all these rectangles going on forever is less than the area under a curve that looks like this and goes through the upper right corners of those rectangles, and if the area under that curve is finite, then the area of all those rectangles is going to be finite. Hey, that sounds like an improper integral. The area under the curve, where the curve goes on forever, that would be found with an improper integral. What curve would look like that? A little bit of thought reveals y equals 1/x². It has a graph that looks like that. Why 1/x²? Well, this is 1/k². And yeah, the value of that function when x is 2 is 1/4. The value of this function when x is 3 is 1/9. The value of this function when x is 4 is 1/16. This function has a graph that does go through the upper right corners of these rectangles. So if the area under that graph extended out forever is finite as an improper integral, that would mean the area of all the rectangles going out forever is also finite. But you already know the integral of that is finite. What is it? It's an improper integral. We can calculate it as a limit, and that limit does exist. We did this before. Functions like this where the power there is bigger than 1 result in improper integrals like this that do converge. This one will converge. What does it converge to? You actually have to calculate the limit. Write the improper integral as a limit like this, and you should write your limit signs. And carry them along until you actually take the limit. Find your antiderivative of x to the negative 2. You're going to get negative x to the negative 1. Evaluated from 1 to b. That's a limit as b goes to infinity. Now plug in b. You get negative 1 over b. And subtract what you get when you plug in 0, or 1, excuse me. Careful about minus signs here. This is the limit as b goes to infinity of 1 minus 1 over b. 1 over b does go to 0. This limit is 1 minus 0, which is 1. Therefore, the area under this curve, this black curve here, is finite. It's 1. Therefore, the sum of the areas of all the rectangles must be finite as well, and in fact, less than 1. Therefore, the original sum must be less than 1 plus 1, 2. And it is. Pi squared over 6 is less than 2. Add on the 1 at the beginning now. Since this sum, starting at 1/4, is less than the area under the curve, which is 1, add on the 1 at the beginning, the entire sum is less than 1 plus 1 is 2. Now that's not a proof. It's a plausibility argument based on a graph and based on a calculation. However, we can use a theorem in the book in section 9.3 to make it an official proof. The theorem is called the integral test. Integral test. It says, suppose there are different ways of writing this. F of x is defined continuous and decreasing on, let's just make it a specific interval here, the interval from 1 to infinity. Have you seen this notation before? I don't think I'd use it here. This is notation meaning the interval on a number line starting at 1, including 1 because it's a square bracket, forever to the right. Infinity is not a number, so when I put an infinity in a curved bracket here, it just means this is an interval that goes forever to the right. X is greater than or equal to 1, or 1 is less than or equal to x. There's another way to write it. There's two statements you can now write based on this situation. If the improper integral from 1 to infinity of f converges, then the corresponding series, k goes from 1 to infinity, of f of k, k is an integer here, that I'm plugging in 1, 2, 3, 4, 5, 6, etc. Up here, x was a continuous variable. It could be anything greater than or equal to 1. Down here, k is an integer, 1, 2, 3, 4, 5, 6, etc. That corresponding series converges. The corresponding limits of partial sums exists. On the other hand, if the integral diverges, the improper integral diverges, then so does the infinite series. Plug k into f. That diverges too, as an infinite series. The corresponding sequence of partial sums diverges. So if we believe the integral test, and you should believe it, it is true. We aren't proving it. It can be used to prove that this series converges. How? Well, you've got to set it up. You've got to say what f of x is. And verify that the integral of f of x converges. What is f of x? How about 1 over x squared, just like over there? You start by saying let f equal 1 over x squared. That is certainly continuous, decreasing function, non-negative. I should say non-negative as well, sorry. Non-negative. And decreasing on the interval from 1 to infinity. Its graph looks like this. You know that. And its improper integral from 1 to infinity does converge to 1. You can say, therefore, by the integral test, this series also converges, though it doesn't tell you what it converges to. Let me say that again. You might want to be writing as I talk. If you want to apply the integral test to prove this series converges, you need to say let f of x equal 1 over x squared. Note, hey, that's a nice, it's defined on the interval, it's continuous there, it's non-negative, it's greater than or equal to 0. And decreasing on this interval, there's what its graph looks like, and you know that. And the corresponding improper integral converges. Therefore, by the integral test, this series converges as well.
So, will the improper integral and the series converge to the same number?
Good question. No, they don't. This integral converges to 1. This series, as we saw on Mathematica, converges to pi squared over 6. And that's not even less than 1. So we're not saying here that the sum is less than the integral. We're just saying if the integral converges, the series converges. If the integral diverges, the series diverges.
Okay, thank you.
Which does mean you can apply this test to an entire family of infinite sums, infinite series. When I say infinite sums, I mean infinite series of this form. We know that the improper integral of this converges if p is bigger than 1 and diverges if p is less than or equal to 1. It converges if p is bigger than 1 and diverges if p is less than or equal to 1. The same can be said about this. This converges if p is bigger than 1 and diverges if p is less than or equal to 1. Though actually if p is negative, you can't use the integral test to prove that. but it's still true. It's a divergent p is negative. Typically, we only consider positive p's when we write this. Hang with me for a few more minutes here. Those series, the sum of 1 over k to the p power, have a name. They're called, creatively, p series. How creative? P. Oh, they could have used a different letter. They could have used a q, and then they call them q series. Okay. Well, they're called p series. Again, they converge if p is bigger than 1, and they diverge if p is less than or equal to 1. It is interesting that if p happens to be an even integer like 2, it can be proved that you always get convergence to a rational multiple of pi to the same power. So if I add up 1 over k to the 4th, I should get a rational multiple of pi to the 4th. And you do. If I add up 1 over k to the 20th, I should get a rational multiple of pi to the 20th. And I do. That's pretty amazing. You can extend Euler's methods to prove that. But if you replace p with an odd power that's bigger than 1, like 3, it turns out there's no simple expression for this in terms of a rational multiple of pi to the 3rd. It does converge to something. The official name for it is zeta of 3. You can approximate that. It's about 1.20206. And if p, remember, if p is less than or equal to 1, like 1, if I add up reciprocals of the integers, that turns out to diverge, and Mathematica knows that. Sum does not converge. That particular series has a name. It's called the Harmonic series. It's very famous. Got a name. Is it related to music? Harmonic series. I think it is related to music, though I'm not exactly sure how. Why this series is related to music when the others are not. Do you know how?
It's related to the notes of waves, sound waves.
Sound waves, okay. So it's related to music, related to sound. It does not converge. It's called the harmonic series. It's 1 plus a half, plus a third, plus a fourth, plus a fifth, plus a sixth, etc. If you look at numerical evidence of whether it converges or not, it's hard to tell. In fact, you can't tell for sure if it converges or not, but it is known to diverge. Let me just spend 1 minute with one more thing. This zeta function is very famous in modern math. It's related to something called the Riemann hypothesis. And as of 2016, as far as I know, nobody has ever proved the Riemann hypothesis. People have tried. If you were to succeed in proving the Riemann hypothesis, you would be world famous. You'd get $1 million prize. There's $1 million prize for it. And you, like I said, you'd be world famous, okay? Don't kid yourself, it involves very, very difficult math to try to prove it. It's related to the zeta function. It is the most famous unsolved problem in math, in my opinion, as far as I can tell, in 2016. It sounds really strange. It says, in effect, the zeros of the zeta function that are not negative numbers all lie on a line in what's called the complex plane, where the real part is 1/2. As strange as that sounds, and you may have no idea what that means. As strange as that sounds, as weird as that sounds, about the zeta function, it is actually important for applications because it's related to prime numbers and how prime numbers are distributed. And that is very important for cryptography. See, codes, which is fundamental to keep your transactions safe on the internet. Okay, so this zeta function, through a long chain of difficult math, at least as of the moment when there are no quantum computers that really are working like people hope they will, as of the moment keeps your internet transactions secure. Amazingly enough. It's related to zeta. And that's what I'll end with today.